V1, V2, V3. Span of V1, V2 equals span of V1, V2, V3. Now we have two vectors like V1 and V2. They span H. Furthermore, they are independent. So these two vectors, V1 and V2, satisfy both conditions that we are looking for. V1 and V2 satisfy both conditions of a basis. So they form a basis, right? So a basis for H consists of V1 and V2. Is it clear to you? Or should I repeat it?
Please, Doctor, again.
Doctor,
Repeat
some of us,
again.
we have no picture actually.
Picture by picture, you mean a slide?
Yeah, we have no slide.
So I don't know. It's maybe there is something wrong with your connection.
Doctor, please, can you repeat? I
Okay,
have
I
no
will.
picture on your slide.
The slide is found.
Can
Can you refresh this?
I refreshed the slides. I hope you all can see it.
No slide, doctor.
But I don't know. Maybe it's because of some problem in your.
We have this slide, yes, now.
You have
Found.
many of you have a slides. They can see a slides. Okay, so let me repeat it again. We have three vectors, V1, V2, and V3. And H, a subspace like H, is defined as the span of V1, V2, V3. And we want to find a basis for H. A basis should satisfy two conditions. First, the vectors in the basis should span H. Second, the vectors in basis should be linearly independent.
بس لا هذا مالتك.
Okay, so V1, V2, and V3. These three vectors satisfy the first condition. They span equals H. But they miss to satisfy, they miss the second condition or property. They don't satisfy the second condition. They are not linearly independent, right? V1, V2, V3 are not linearly independent because as you may notice, V3 is a linear combination of V1 and V2. Right? So, what's the solution? The solution is to find a subset of V1 and V2 and 3 which form a basis for H. Which subset? Actually, from this set V1, V2, V3, we can remove or discard those vectors that are linearly dependent to the others. In the previous theorem, we learned that we can do this safely without any problem of reduction in the span. So in the previous theorem, theorem 5, we learned that if a vector is linearly dependent to the other vectors, it can be safely removed without resulting any reduction in the span. So V1, V2, V3. V3 is linearly dependent to V1 and V2. Why? Because V3 equals 5 V1 plus 3 V2. So we can safely remove V3 from this list. We will have V1, V2, two vectors now, not three vectors. Okay, so these two vectors, V1 and V2. S-span of V1, V2 equals S-span of V1, V2, V3 equals H. Why? Because V3 is linearly dependent on V1, V2. Okay, so the first condition of a basis is satisfied by V1 and V2. They span H, right? They span the whole H. What about the second condition? The second condition says that V1 and V2 should be linearly independent, and they are. They are linearly independent. So V1 and V2 satisfy both conditions of a basis. So they form a basis for H, right? So a basis for H consists of V1, V2. Is it clear now? It's very simple. Those vectors that are linearly dependent to other vectors should be removed. That's it. Why? Because their reduction don't, their removal don't result any reduction in the span. After removing them, we wouldn't have any reduction in the span. Very simple. So we can safely remove them. We can safely remove those vectors that are linearly dependent to the others. Until we reach to a set of vectors that are linearly independent. So no vector of this set can be removed. This set forms the basis. Very simple. Right?
Sorry, doctor, we have a question.
Yes.
Doctor, why we set 0 V3, but in the equation we have vector of V3, 16 minus 5. Why we put 0 V3?
We don't look at this explanation. You pay attention to what I said. But if you really care about this explanation in the slide, because it wants to say that any vector which is a linear combination of V1 and V2 is also a linear combination of V1, V2, and V3. Okay, so yes, any vector which is a linear combination of V1 and V2, it is a linear combination of V1 and V2 where the weight of V3 is 0. Very simple. And then in the rest of this argument, it says that any vector which is a linear combination of V1, V2, and V3 is also a linear combination of V1 and V2. So S-span of V1, V2 equals S-span of V1, V2, V3. Actually, over here, first, it shows that any vector which is a linear combination of V1 and V2 is also a linear combination of V1, V2, V3. Then it shows that any vector which is a linear combination of V1, V2, V3 is a linear combination of V1 and V2. So S-span of V1, V2 equals S-span of V1, V2, V3, because any vector in S-span of V1, V2 is also in the S-span of V1, V2, V3, and vice versa. Any vector which is in the S-span of V1, V2, V3 is also in the S-span of V1, V2, right?
Yes, it is clear, doctor.
Okay, great. Okay, let's move to the next point. Next point Next point says how to find a basis for column space of a matrix. So if you remember, we have a matrix, and this matrix has three famous subspaces. One of them is column space, the other one is null space, and the third one is row space. What is column space of a matrix? Col A or column space? I explained
Call A.
col A. What is col A? What is col A or column space of the column space of A?
Doctor, it's a span of A1 to AN.
Yes, it is the span of A1 to AN. It is the set of all linear combinations of A1 to AN, right? Okay. Col A is a span of A1 to AN. Col A or column space of A is a span of the columns of A, or equivalently the set of all linear combinations of the columns of A, right? What is null A? Who can say what is null A?
Doctor, null A, the null A space of an M multiply M matrix A. Set of
Please
all
repeat.
okay, set of all vectors in span.
Please repeat it again.
Null space of matrix N multiply N of A matrix A.
Null A actually is the set of all solutions of homogeneous system X equals 0, right? The set of all vectors that are mapped to 0 by A. The set of all solutions of Ax equals 0. This is called null A, or null space of A. I repeat it. Null A or null space of A is the set of all solutions of Ax equals 0, right? Okay. And what is a row A? The row space of A or row A. So in row A, we consider each row as a vector, and row A or a row space of A is defined as the set of all linear combinations of the rows of A, or equivalently, it is defined as the span of the rows of A. Okay, so row A is defined as a span of rows of A. Col A is defined as a span of columns of A. Okay, so now we want to find a basis for col A. We want to find a basis for col A. We have a subspace like col A, column space of A, and we want to find a basis for col A. Theorem 6 helps us to find a basis for col A. So it says that pivot columns of A form a basis for col A. We don't prove the theorem for you. You don't need to know what is the proof, but I describe it. So you have a matrix. You want to find a basis for its column space. What you do is that first, let's call this matrix A. First, find its echelon form. You find echelon form of A. This is A. You find a matrix like B, which is echelon form of A. So in matrix B, you can see what columns are pivot and what are non-pivot, right? In echelon form, you can see what columns are pivot and what columns are not pivot, right? So those columns that are pivot, you write their number, their index. For example, column number 1, column number 3, and column number 4 are pivot columns. And column number 2 is not a pivot column. Then you get back to the original matrix A and columns with those pivot numbers form a basis for color space. So in matrix A, column number 1, column number 2, and column number 4 form a basis for color space. Actually, the reason that you form matrix B, the echelon form of matrix A, is that from matrix A, you cannot determine based on matrix A, based on original matrix A, you cannot determine what columns are pivot and what columns are not. So you need to compute echelon form matrix B in order to be able to determine pivot columns and non-pivot columns. After finding the number or index of pivot columns, you get back to the original matrix A, and in that matrix, you choose those columns with the numbers, with the pivot column numbers in B as the basis, right? So the vectors or the columns are chosen from A. But the numbers or indices are determined in matrix B, right? So let me see if we have an example. Not here, not here. Let me find an example or just a second so that okay. If I can find an example, you no example. The thing is that writing over here is difficult. And so I'm trying to find an example in the slides. If we do not have examples over here, we may okay. Over here we have an example, but let me if I can explain this example. Okay. So great. We have example. We have a matrix like this. Do you see this matrix? Matrix A? Do you see it? Do you see this matrix?
Yes,
Yes,
doctor.
we see. Yes.
Okay, so we have this matrix, and we want to find a basis for its column space. You know what is basis, right? What is the definition of basis? So this is A, matrix A, the original matrix. We compute its echelon form. Ignore this last row. You don't pay attention. You don't need to pay attention to this last row. Last column. Sorry. Just ignore this last column, right? So the rest of this matrix is the echelon form of matrix A. So you call this matrix B. You have matrix A, the original matrix, and you find its echelon form like this, matrix B. So in matrix B, what columns are pivot? In matrix B, what
Column
column?
1 and 3.
1 and
3. It's a
yes,
pivot.
yes. Column 1 is pivot because it has a pivot position, leading element. Column 2 is not a pivot column because it doesn't have a leading entry. It doesn't have a pivot position. Column 3 is a pivot column because it has a pivot position. And column 4, column 5, they don't have pivot positions. They don't have leading entries. So they are not pivot columns. So column number 1 and column number 3, they are pivot columns. Now let's get back to the original matrix. We have number 1 and we have number 3. We choose these two vectors as the basis for the column space of A. That's it. So if in the exam, you don't need to know the proof because proof is very long and probably a bit complicated. You then know theories and proofs that much. So let's just know what is the procedure for finding a basis for column space of a matrix. We may ask this question, we may give you a matrix in the exam and ask you to find a column, a basis for the column space of this matrix, right? So you should act in this way. You should first convert this matrix into its echelon form, like this, and then find in echelon form what columns are pivot. Column number 1, column number 3 in this example. And then get back to the original matrix and pick columns with those numbers, number 1, number 3, as basis for column space. Right? Is it clear?
Sorry, Doctor, not sure not sure screen presentation. Just voice.
Sorry? You don't see the presented slides.
Yes, not sure. Just voice. Your voice.
But I think the rest are seeing the slides, right? Most of you are seeing the slides, right? I can share it again. I can stop and then share it again. I hope this solves your problem.
Okay.
Okay, do you see the slides now?
Yes, we have.
Okay, so everyone, does everyone see the slides?
Yes, doctor.
Yes, doctor. Yes, doctor.
Great, great, great. So, is it clear to you to find a basis for the column space? Is the
Please,
example
doctor.
clear to you?
Please,
Okay.
doctor, repeat again, please,
Repeat again
because
what?
the doctor was not found.
Okay. Okay, we have a matrix like this, A, and you are asked to find a basis for its column space. What you do is that first find its echelon form. So ignore the last column in this matrix, and the resulting matrix is the echelon form of matrix A. Let's call it B. So in matrix B, you check what columns are pivot. Column number 1 is pivot. Number 2 is not. Column number 3 is pivot. Number 4 is not. Number 5 is not. Columns number 1 and number 3 are pivot. So you choose these two numbers and get back to the original matrix, matrix A. So in this matrix, columns with these numbers, number 1 and number 3, these two vectors form a basis for the column space of this matrix. So this vector minus 3, 1, 2, and this vector minus 1, 2, 5 form a basis for column space of matrix A. That's it. Is it clear now?
Yes, doctor. Yes, thank you.
Okay, great. Okay. So, okay, great. So let's move to the next point.
Vector space.
Next point is about coordinate systems. I don't know, maybe in Arabic you call it mukhtasat. Mukhtasat. Do you have this word in Arabic? Mukhtasat.
Yes, doctor. Yes. مختصات.
Mukhtasat. What does it mean? Mukhtasat, what does it mean?
Specify.
Summary. Summary.
So you have a point in some, I don't know, R2 space, for example, and the mukhtasat of that point. What does it mean?
Which word in English, doctor? Representation?
No, you have a point. You are in R2 space, right? You are in R2 space, like in Orly-Dossy space, Euclidean space. And you have a point in that Orly-Dossy space, in Euclidean space, in R2 space. You have a point in R2 space, and you want to find mukhtasat of that point. Let me draw something. So this is some R2 space, and this is a point. And you want to find mukhtasat of this point, or coordinate of this point. Actually, mukhtasat of this point is a vector of size 2. For example, its x mukhtasat is something like 3, and its y mukhtasat is something like 1. So you have 3, 1 as coordinate or mukhtasat of this point. Isn't it familiar to you? Suppose that we have a subspace like V, or a vector space like V. We have a basis for this vector like we want to be in. We have a subspace like V, any subspace that you may imagine, like R2 subspace, R3, and etc. And we have a basis for this subspace, V1, V2, etc. Bn. This set of vectors form a basis for subspace. This theorem, theorem 7, says that any vector in this subspace V can be uniquely written as a linear combination of V1 to Vn, right? So we have V1 to Vn. V1 to Vn is a basis for V, right? So a basis has two properties. What are these two properties? What are two properties of a basis? I explained in the beginning of the class.
Must be Babbitt column.
Two conditions, doctor.
Contain the Babbitt column.
So V1 to Vn actually are basis for V if these vectors, if this set of vectors satisfy two properties. First, they expand V, they expand the pool of V, which means expand of V1 to Vn equals V. Second, V1 to Vn are linearly independent, right? So the first condition of property, V1 to Vn expand V. What does this imply? V1 to Vn expand V. What does this imply?
Could you repeat, doctor?
B1 to Bn expand V. So B1 to Bn expand V. What does this imply?
It's a mapping.
It implies that any vector in V
Can determine.
can be written as a linear combination of B1 to Bn. Right? This definition of expand, right? When B1 to Bn expand V, it means that any vector like X in V can be written as a linear combination of V1 to Bn. Actually, you have something like that. It can be written as a linear combination of V1 to Bn. Any in V, any arbitrary X in V can be written as a linear combination of V1 to Vn. Right? Why? Because V1 to Vn is expand V. Right? Definition of expand. So any member X of V can be written as a linear combination of V1 to Vn. Actually, this theorem 7 proves that if linear combination is unique, then V1 to Vn is a basis, which means more than expanding. It also has the property of independence. Any vector X can be uniquely written, uniquely written as a linear combination of V1 to Vn. This means you don't have two different linear combinations of V1 to Vn that give you the same vector x. This is a very important property. So then you have a basis for a subspace like V. Any member of subspace like X can be written in a unique way in terms of a linear combination of the bases. So actually what this theorem says, if you have this equation 1, if you have this linear combination x equals c1 b1 etc cn bn, and then you have another linear combination which yields x equals d1 b1 plus etc dn bn, then c1 should be the same as d1. C2 should be the same as D2, and Cn should be the same as Dn. These two linear combinations should be the same because D1 to Dn is a basis, and any member like X can be uniquely written as a linear combination of D1 to Dn, right? So this unique linear combination or this unique representation of each vector x is called its coordinate vector, or it's called its coordinate relative to basis. All right, so you have a basis, you have a vector like x. You can write x in a unique way in terms of linear combination of vectors in B. The weights of this linear combination, which is a unique vector, is called coordinate of x according to B or relative to B. All right? Is this clear to you? So let me give you a simple example, a very basic example. You have, let me do something. You are in R2. You are in R2, right? You are in R2 space. And you have this point. And in R2, let's have two vectors like E1 and E2, the standard basis. E1 is 1, 0, and E2 is one combination of E1 and E2. For example, this one equals 3 times E1 plus 2 times E2, right? Because we have here, and this is 3 times E1, and we have this, and this is 3 times of E2, right? Okay, so this point equals 3 times of E1 plus 2 times of E2. And this linear combination for this point in terms of E1 and E2 is unique. You can't find any other linear combination for this point in terms of E1 and E2. These two weights 3, and 2 are unique. So you call this unique vector 3, 2 as the coordinate of this point. You call this point x. So the coordinate of x in basis consisting of E1 and E2 is 3, 2, right? So you have something like this. X, you have x, then coordinate of x in B equals 3, 2, right? And B over here consists of E1 and E2. B has two vectors, E1 and E2, and coordinate of x in this basis is vector 3, 2. Why? Because x equals 3 times of E1 plus 2 times of E2.
This example only?
No, in general, the course discussion, another session will start in 4:30, 4:32, 4:35, let's say, and it will end at 5, near to 6. It will finish at 6.
Also 1 hour.
1
half?
hour and yes, 1 hour and 20 minutes.
It's very tired for
It would be a complete session, right? It would be a complete session of. So, okay, is it
Doctor,
fine?
can be the session will be tomorrow?
Tomorrow is a holiday.
Yes, Doctor. Not today.
Tomorrow is a holiday.
Doctor,
Yes.
because we are returned from our job now, and we are listening at your session, Doctor, from 3 up to now. And really, we are tired. We are working from 8 till now, and we cannot continue to another 1 hour. We want some rest, Doctor. So if you can, please, if you
and
can
Doctor,
move the next session to tomorrow.
and Doctor, we have English, we have Persian language also at 4 o'clock.
You have at 7. Right? Okay. Okay. If you are tired, okay, we can stop here. And for the next session, I will let you know.
After the Eid, Doctor. After the Eid, no problem. After Eid.
Tomorrow is a holiday here, so I'm not sure that I would be able to make it to have a session tomorrow. I will try. Let's see what happens. In
Whole
the
day
case,
for what question, Doctor?
in the case we have a session tomorrow, I will let you know. One of you send me an email. I will let him know tomorrow, probably before noon, and that person inform all of you if we will have a class tomorrow or not. Okay? So one of you send me an email today.
Okay, Doctor.
Now,
Doctor, did
and I will reply to him